Hi, this is Peter Ganji.
And Kevin Katubi at the University of Connecticut with a presentation on the production of BioOil using pyrolysis. The abstract chosen for our presentation was Forest Biorefinery Processes, Wood Extraction and Processing for Biofuels and Bio-Based Products. This presentation will go over various aspects of wood pyrolysis, including requirements for fast pyrolysis, feed processing, some chemistry behind the process, two types of reactors used, and the future of BioOil.
Pyrolysis is a process used to convert biomass, specifically trees and wood chips, into bio-oil and other products. It combines high heat and special reactor designs in an oxygen-free environment to break bonds in cellulose and lignin.
Some of the general requirements for the pyrolysis of wood include high temperatures of over 400 degrees Celsius, a high rate of biomass heating, usually from fractions of a second to just a few seconds. If the biomass is heated for too long, the polymers in the wood will break down too far, creating permanent gases, as opposed to the high molecular weight compounds found in useful BioOil. Another requirement is the immediate quenching of the hot product vapors so that they condense into oil. Also, various reactor designs require specific biomass size, ranging from less than 2 millimeters to as large as 20 millimeters. In the process of pyrolysis, the polymers that make up plant cell walls, lignin, cellulose, and hemicellulose, are cleaved into a myriad of different chemicals that include acids, alcohols, esters, sugars, aldehydes, phenols, aromatics, etc. There are 300 known chemicals in BioOil.
The process of wood pyrolysis is done in 4 general steps. The first is the processing of the biomass into feed for the reactor. Next is the actual pyrolysis reaction where the biomass is vaporized. Following the reaction, the product vapors are condensed and byproducts such as char are filtered out. Finally, the product gases and char are burned to help heat the pyrolysis chamber, and all that remains is the desired bio-oil. In this presentation, we will go over 2 specific types of pyrolysis.
The biomass preparation takes place in 2 parts. The first is the reduction of the particle size. Subsequently, the feed is dehydrated a significant amount. Particle size is a key issue when selecting a reactor type. The smaller the particle size, the more expensive the processing costs.
There are 6 reactor designs for producing bio-oil: bubbling fluidized bed, ablative, circulating fluid bed, rotating cone, vacuum, and transported bed. In this presentation, we will go over the use of the bubbling fluidized bed and the ablative process.
A process schematic for the first process, the bubbling fluidized bed reactor, is shown here. In a bubbling fluid bed design, tiny particles of biomass are suspended by a hot inert gas. The high gas flow rate creates a vigorously bubbling mixture of gas and solid biomass particles. The dynamic motion of the fluid bed allows for uniform temperature, which can be easily controlled, ideal for biomass pyrolysis. The gas flow rate controls how long the biomass and resulting vapors are heated, allowing for perfect heating times. Some of the benefits of the bubbling fluid bed reactor are as follows. It is self-cleaning. The reactor is not substantially deteriorated by the reaction, and complete control over particle heating. Some of the downsides include small particle size of less than 2 millimeters, and some difficulties that arise in separating the product vapor and carrier gas.
Ablative pyrolysis is a process in which biomass particles are melted and vaporized. Initially, biomass particles are inserted to a small chamber which is occupied by fast-moving gases such as nitrogen. These gases carry the biomass into a tubular apparatus called the vortex reactor, which has been heated to 625 degrees Celsius. In the vortex reactor, biomass particles spin around very fast along the edges of the chamber. The heat within the chamber, as well as the friction from the reactor's walls, is enough to melt and vaporize the biomass. If any biomass solid remains after this, they are filtered out and automatically undergo the process once again. After this filtration has occurred, vapors are then redirected to other sections of the machine where char and other byproducts are filtered out. Finally, remaining vapors will condense into BioOil. There are two main disadvantages to the process. The first is that vapors sometimes will accidentally get recycled through the vortex reactor twice, which overheats the vapors and severely damages them. In addition, the biomass travels into the vortex reactor very quickly and at a perpendicular angle to ensure that each and every particle of biomass undergoes the heat released by the friction of the inner walls. However, this transition from linear to angular momentum causes significant erosion in the vortex reactor. This erosion adds to maintenance costs. The advantages of the process are that it can use particles up to 20 millimeters in size, which is much larger than other means of production can support. This will be helpful in the mass production of BioOil. In addition, there is hardly any waste in production. All of its byproducts, such as char and gases, are used to heat up the vortex reactor. Essentially, the only product of the process is BioOil. BioOil has a number of uses. The first is diesel engines. BioOil alone cannot be used as fuel for engines. However, studies done by the University of Kansas and MIT have shown that if BioOil and normal diesel fuel are mixed in a 1-to-1 ratio, this combination fuel works just as well as pure diesel fuel. BioOil can also be used for fuel and combustion turbines. These turbines are used to power aircraft, trains, ships, and generators. Furthermore, BioOil has the potential to become a much finer oil such as petroleum. To do this, one could dilute the BioOil with alcohol solvents. Adding these solvents add complexion to the BioOil so that when it is used as fuel, it has more capacity to combust. In order to expand the future of BioOil, there are certain measures that can be taken. First, further interest should be taken into making BioOil a more efficient fuel. Also, environmental and health regulations for BioOil production and exposure need to be much more defined than they are now. And lastly, BioOil production facilities are very expensive to build and maintain. A long-term supply for the production of BioOil is necessary in order to spark interest from investors. It has been suggested that a 10-year guarantee would be enough to spark this interest. Thank you for listening to our presentation, and we hope you enjoyed it. Are there any questions?